Great. Thanks so much, Chris, for the very kind introduction, and thanks for everybody for coming out. So in computer vision today, we still get a lot of our supervision from humans. Traditionally, this was from things like labels, segmentations, attributes, but there's been a recent movement to try to reduce the need for the supervision, typically by using things like implicit supervision from language. And while we often think of this language as being a free sensory signal that we get with zero cost, it actually has a lot of the same limitations as this traditional form of labeling. Under the hood, you need a lot of people to provide you with language. It's a lot of work to get this data. And you're stuck only with the information that's gone through a human's head, giving you a kind of arguably high-level form of supervision that may sometimes be imprecise. And there's a lot of other issues. There's only a limited amount of this data. And maybe most worryingly, it's very hard to learn from language autonomously. If you can imagine a robot that's trying to explore the world and navigate around, and it has to phone home to humans every time it needs to learn anything. It seems like a very unsatisfying state of affairs. And this way of learning is very different from the way humans, they might get some information from their parents who tell them the names of different objects, but largely they're learning by exploring and receiving. So she's learning about the world through sensors. She's finding correlations between sight, sound, and touch. And so you can ask, if we're building these so-called foundation models, largely using tools like language, there's a real worry that we're building them on shaky foundations. We have systems that are learning from really two extremes. We have very high-level supervision that we get from labels and language, which are arguably hard to learn from autonomously and provide very high-level information. And at the other extreme, we have models that learn from images alone, which is a very inefficient way to learn. Now, to be clear, I'm not saying there's anything wrong with these language-based systems. In fact, I made this using text-to-image models like DALL-E. But there's this missing middle of supervision that comes from sensory modalities, information like motion, sound, and touch. And today I'm going to talk about our work on developing algorithms, data sets, and models that can learn from this form of sensory supervision in lieu of human-provided supervision. So I'll start off by talking about our work on learning through motion. I think this is probably the most familiar learning signal amongst these. And when objects move through the world, they inevitably change their appearance. They'll deform, they'll get relighted, you'll see them from a different perspective. And so if we could just learn these changes, then we could get a free learning signal from video. And really at the core of this problem is finding space-time correspondences. We're figuring out what goes where over the course of video. Now, of course, this is a classic computer vision problem, and there have been tons of different approaches for solving it over the years. But unfortunately, all the different approaches tend to be very special purpose, and they tend to be addressing a variety of different specific tasks. For example, on the one hand, you have optical flow models, which give you very dense motion predictions, but they tend to be very short range. At the other extreme, you have tracking methods that will track objects over long horizons, but they tend to be relatively sparse. And each of these different tasks has its own special purpose data sets, models, algorithms. And so let's see if we could learn space-time correspondence in a more general purpose way by using tools from self-supervised representation learning. Could we create unsupervised learning algorithms that learn feature representations that are useful for a variety of motion analysis tasks? And so this is some work that was led a few years ago by Alan Jabri and in collaboration with Alyosha Efros, both at the time at UC Berkeley. And we have an idea for approaching this problem using what we call palindrome videos. We'll take a video that's going forward in time, and then we'll reverse it, creating a sequence that goes like frame 1, frame 2, frame 3, then back to frame 2, back to frame 1. And we'll train a tracking model to track forward in time through this video, then backwards in time. And we'll train it to be cycle consistent. It should end up at the end of the sequence back where it started. You go forward to frame T, from frame T to T plus K, then back to frame T, and you should end up exactly at the patch that you started. And the benefit of this approach is you can train models entirely from unlabeled data, and you can, it has very few underlying assumptions behind it. And so to be more concrete on how we train such a model, we create a graph where each patch in a frame becomes a node, and we'll assign a feature to each one of these nodes, just using a simple residual network. Then we'll define a graph on these nodes where there's an edge that connects every node in adjacent frames together. And we'll define a transition probability for a random walk on this graph. A random walk that starts at one patch will move to a patch in the next frame with probabilities that are indicated by softmax attention. We'll take a dot product between the embedding vectors in the patches, and then that'll indicate how likely the patch is to transition to that future frame, and we'll normalize these to sum to 1 using a softmax. And so this graph and this transition probability gives us a distribution over possible trajectories for this patch over the course of the video. If we just see where the patch moves, and that tells us what the corresponds. And so our goal is going to be to learn transition probabilities that lead to cycle consistent tracks. And we can take advantage of the structure of this problem here. Because this is a Markov chain, we can chain together adjacent transition matrices to give us transitions from a given frame to future frames. You could just multiply the transition matrix from frame T to T plus 1, T plus 1 to T plus 2, and so on, until we've reached the end of the sequence. And our goal then is going to be to learn image features that lead to good transition probabilities. And in particular, these transition probabilities should give us cycle consistent tracks. They should give us the same track going forward in time as back. And if you can write this out, use a very nice, simple objective function. We're going to take a transition probability from frame T to frame T plus K, then go back from frame T plus K to frame T, and we're going to want the diagonal of that matrix to be as large as possible. Because we want to assign as high return probability as we can to walks on this graph. So, so just a quick summary then, we're learning image features such that when we plug them into this random walk, we end up with high probability of returning what we started. It ends up with this nice, simple objective function that, if you're familiar with contrastive learning, is quite similar to the loss functions that you may have seen.
Andrew, are these matrices like single stochastic or double stochastic?
Single stochastic. Okay. Yeah, we actually, as I said, we have a variation of this that uses Sinkhorn, which you can consider formulations where you try to learn a bistochastic matrix in a similar formulation. It didn't work as well, but I think that's a really interesting approach as well. And if it's working well, it should be kind of close to, probably be close to bistochastic.
Is the number of nodes in the graph fixed in pre-specified a priori? How does it change for, say, different meters of different sizes?
That's a great question. So in this initial work, we followed other work in tracking. We have actually a very coarse patchification of the image. We're going to take the image, chop it up into a 7x7 grid, And at training time, that's all we use. At test time, though, you can run it at higher resolution. You can sample the patches more high res and get better, more granular patches. But we'll talk in a second about how you do it.
And the meaning of the IJ entry of the matrix A is just the probability of transitioning from node I to node J.
Exactly. Yep. And when you, I guess in these matrices, that would be the probability of transition from this patch to this other patch in these adjacent frames. When you multiply the matrices together, we have this the special matrix that's indicating the probability of a very distant transition.
And why that loss is adequate? I expected that you would have wanted maybe the transition probabilities to not change too much with time.
Yeah, so that's a good point. Like slow features kind of there's a long history of really interesting formulations there. But I guess what's tricky is the transition probability, objects move around. And so if you're measuring the similarity at the level of matrices, it's a little weird because now the rows have different meanings. Objects might have moved in between them. But something like slow features very much is along those lines. If it's a high enough frame rate.
Perhaps can you comment on what the objective measures?
Yeah, so this objective says we're going to transition from frame T to frame T plus K using the random walk that's given by our features. Then we're going to go back from frame T plus K to frame T. And then this gives me if I look at that matrix, this is how likely is it that each patch in this initial frame transitions back to itself, if I look at the diagonal of that matrix. The log here is just to get a cross entropy loss, because we'll use log loss on those probabilities, and we're looking at the trace, we're just looking at the bag. So it's a pointwise log here.
And is the idea that you're going to use this for all possible values of K?
Yeah, actually, we do that. You can actually do it with just a single fixed K, but we actually, what's nice is once you have these matrices, you can compute all K very efficiently. You just need to multiply some matrices. And you can still learn from long sequences. The long sequences will supervise the short sequences and vice versa. Great. So this is
Andrew,
yeah.
you mentioned that this is really close to kind of contrastive learning style objectives.
Yes.
Is the intuition there just that you're trying to match each patch to itself rather than to other patches? You're measuring only the diagonal.
Exactly.
Yeah.
So
is there a kind of deeper connection there? Does it actually reduce to something that looks like a contrastive learning kind of object?
Yeah, so if you just looked at, so typically in contrastive learning, you would take your image, then you'd augment it in a whole bunch of different ways. You crop it, change the colors and so on.
Yeah.
And then you'd end up with a matrix similar to this one, where the rows correspond to each image and the columns correspond to every other image.
So the evolution
and you want
the augmentation that you're.
That's right. Yes, we don't have to do augmentation here because the video gives you that augmentation for free. And so if you were to kind of this objective, you'd see in contrastive learning, but there'd be like a single matrix. They don't usually write it that way. But
yeah,
you could. Yeah. Great. So at the time, this was from around 2020, and at the time, this was state of the art for self-supervised methods amongst a segment propagation task. So if you had, thank you. If you had a segment in an initial frame and then you propagated it in the future using the transition matrix, and with some special handling for occlusion, you could propagate that segment to these future frames more effectively than previous methods. But if you look carefully, you can see it's still kind of coarse. It's really, and as was pointed out, the patches it was trained on were relatively coarse. You don't get a really fine-grained motion. Something like optical flow, by contrast, would give you much more precise motion, even if it would struggle with these longer transitions. And so we wanted to see if we could improve this model by incorporating the tricks from classic optical flow methods. And in particular, we'll use a multi-scale matching. We'll perform our matching at a patch level initially. Then we'll recenter our match wherever we ended up. And we'll perform another contrastive random walk at a finer scale and repeat. This was led by a former master's student of mine, along with collaborations with the others. And so in each scale, we'll perform a single contrastive random walk, and we'll reinitialize the walk at the finer scales. And we therefore end up with a loss that sums over L different scales. We used 5 different scales in our experiments, and we got an improvement each time by adding scales. And we also incorporated other tricks from optical flow, because this is hard to optimize on its own. In particular, we use a smoothness loss. In other words, the motion of the patches should be spatially smooth. 2 patches that are next to each other should move in the same way. And we also use the architectures that have been proposed in the optical flow literature. So in particular, we adapt this very successful architecture called PWCNet to give us our multi-scale feature pyramid. We also use some other tricks I won't talk about, but I'm happy to discuss. Like we have ways to regress the flows to make them more accurate. And I think what's really nice about this approach is you can perform many different tasks with it. You can perform optical flow just by seeing where the pixels move in between adjacent frames. You're kind of propagating the position over time using this transition matrix. And you can also apply it to tracking tasks just by looking at the transition matrices themselves. They give you the probability of a patch in one frame moving to a future frame. And our model performs pretty well on both styles of task, in particular, amongst other self-supervised methods. So it's not the state of the art on optical flow, but it was maybe on par with the 2019 state of the art, despite being based on very different principles. For example, there's no photometric loss. There's nothing that says 2 pixels should match because they look. We also found an improvement in the error rate as we increase the length of the cycles. Like, as you increase the number of frames that you use for computing cycle consistency, you obtain a better endpoint error, up to 4 frames. And we also found our model did quite well on pose tracking tasks, where it outperformed the state of the art on a self-supervised body pose benchmark called JHM. And I think one of the things that's exciting. Oh yeah.
Could you go back to
sure.
Multi-scale?
Yeah.
Yeah. 2 questions here. The first one is, in optical flow methods, the scales are not fully independent from each other, right? What uses the core scale to initialize the finer scale and so on. It seems to me here that you're treating every scale independently and not just different matrices.
Yeah, that's a great point. We actually have, since we're using this PWCNet architecture, the features at each scale are tied together. So, and we actually do get a learning signal. So we actually back propagate through this entire model. So, they share the same feature, multi-scale feature architecture. It's a bit like it doesn't have the same skin connections, but you can think of a bit like a UNet or something. You have this feature pyramid, and then secondly, when you back propagate, you do go through the entire stack. That being said, I don't think we have very good evidence that that it does the future scales influence the earlier scales, because the operation where you recenter the features is not really very differentiable. And I imagine other optical flow methods probably have the same comment. You're making a hard decision about where the model moves at each scale.
My other question was, if one was doing optical flow and one asked the question, did I move from pixel I to pixel J? And if I wanted to do that in a probabilistic way, one would say something like e to the minus the norm of the optical flow squared, modular normalization, that would give you the probability. So in terms of designing a network, I could design one that predicts directly the A matrix, or I could go back to the old optical flow estimation with neural networks and just have a network that predicts the optical flow, but then put it into an A shape. And therefore one would automatically use the same old machinery that is multi-scale for optical flow estimation with an extra loss, which is this A matrix. So wouldn't that
In case you decide only for one flow, that's the big difference.
Yeah, multimodal distribution.
I don't think I got 3 points.
Here it is everything versus everything, right?
Yes, yeah, so I guess what's nice about this is,
The local area.
like if there are two equally probable locations, I think one of the downsides of traditional optical flow is you have this point estimate of where to go. And you can try to add a Gaussian around that or something, but it becomes very hard, especially if you have like an aperture problem or a uniform area where you're genuinely very uncertain where you are. Whereas this is like you're comparing everything to everything else. You have this sort of non-parametric matching. Great. So one of the things that I think is interesting about these approaches is you can also use them for other modalities. You can see there's very few built-in assumptions on this contrastive random walk. And we can actually apply it, perhaps surprisingly, to sound and to audio-visual data. So one of the most important things you can glean from stereo sound is the time delay of when a sound reaches one ear versus another. For example, if a sound reaches my right ear before my left ear, it's probably on the right side of my body. And if you can just estimate that time delay, then you could predict the azimuth of the sound. A classic signal processing of sounds. And my PhD student, Zeno Chen, along with collaboration with David Foey, we wanted to see if it would be possible to learn to do this time delay estimation using some of the techniques from visual tracking. And here's what I mean by this. Consider the task of predicting the time delay between these two different waveforms. This is the waveform from my left ear, this is my right ear. I just want to, if you think about it, this is a kind of inter-aural correspondence task. I want to find the time step that matches this chunk of the waveform to this other chunk of the waveform and the other audio that I've recorded. And this is like a traditional way people have formulated this time delay estimation task. And if you think about it, very similar to this visual correspondence task. It's almost like I'm going to find the way to match this waveform to that waveform, find the shift that aligns one to the other. And so, just like before, we can use the same cycle consistency idea. We can take unlabeled audio, and we can learn cycle consistent matches between the left and right waveforms in a stereo pair. We're going to take one of the samples in one of the waveforms, do its nearest neighbor search in the other waveform, then go the other direction and see whether we ended up backwards there. Yeah.
So one difference from the visual setting here is that the waveform at any particular time instant is now a superposition of many different sounds.
Yes, that's a great point. Yeah, so as Dinesh was pointing out, you have sound mixtures in general, and so we deal with that. I don't mention, I don't have a slide on it, but we have a kind of, I think, a neat way of dealing with that. We just add synthetic sound mixtures during training.
You know for each component there.
Exactly, much like you would see when source separation, where you can just mix in some background sound. You can also incorporate visual information in a similar way, like localize just the sound of the person you see and not any other sound. If you want, I can chat about that later. There's tricks.
Cool. Yeah.
And so just like before, you can use the same contrastive random walk formulation that we developed for vision. You can compute transition probabilities between features you assign to every time step in the first waveform and second waveform. And like before, you can do a random walk from the left waveform to the right waveform back to the left and try to maximize your cycle consistency. And we can use exactly the same formulation as the contrastive random walk, the same objective function, but your transition matrices go between the left and right waveforms instead of between frames. And yeah.
So here we try to learn the transition.
Yes.
So I wonder, for the objective you have there, it makes sure it's circular consistency, but how it makes sure it's the quality of tracking or matching. So for example, the trivial solution would be all the transition matrices identity.
Yeah, that's a great point. So in practice, if you were able to somehow figure out the location of each time step, then you would be able to come up with a trivial solution where you just predict that there's no motion. And we address that here by simply using basically a fully convolutional network where it doesn't have a receptive field that's large enough to figure out where you are in the full model, or you're using individual patches as well. But there's another solution, which is just to do data augmentation. If you just randomly crop the images, the audio, you can, there's some work from Phil Torr's group that showed that you can avoid these trivial solutions. Great question. Yeah.
And one question, so for the visual tracking, different pixels can be moving in different directions. But if you look at it in this left and right ear sound tracking, they all more or less experience the same delay. How is that modeled in the?
That's a great point. I think if the sound source were moving, then that wouldn't be the case. So if you have like a car that's driving, you'll see in these examples, the time delay will really vary depending on where you are. In practice, we trained our model just on unlabeled music from the internet. In theory, there would be maybe some small amount of motion there, and in practice, I'll show some examples where we tested it on actual motion. But I think in principle it could deal with that. I agree there's less motion in general. But I think the formulation still could handle that. And in practice, when you localize sound, you often do generalized cross-correlation, which would kind of assume there's a single shift for a large segment of the audio. Great, so here's some examples of this model. So I'm going to play, I'm going to show a video. This first one I just recorded on my own. I held up an iPhone to the street as cars drove by. And because the iPhone nowadays has a stereo camera or stereo microphone built into it that's pretty good, you can actually collect sound, the sounds that you can actually localize. So you can see as the car goes from left and right, our prediction of the sound direction moves in a consistent way. And also seems much better than this bigger way than the classic signal processing methods. The difference is much more dramatic when there's background noise. We tend to get become much more robust in those methods when there's a lot of background noise. And here's another example. This is one where there's one we just found on Flickr. We searched for iPhone 12. On Flickr, we found this video of someone moving a camera around where there's a waterfall. And the relative pose between the and the point water. Yeah.
Here you use the difference between left and right on the step.
That's right.
This is in the order of microseconds, or?
Yeah, I think so. Yeah.
And what again? How do you estimate the?
Great question. Yeah, so just using, you can just do feature matching. So every time step in this left waveform, I think we do like every other sample or every fourth samples, which is still, as you're pointing out, a very high sampling rate, 16,000 hertz, and then you're sampling, depending on the model, 1 out of every 2 samples. So you have like a very high sampling rate for the audio, and you're slicing the waveform at that point, computing features for it. And then to do the matching, it's just like you do in visual tracking. You take those features, you slide them over the other features in the other waveform, and you measure their similarity. And I didn't mention it, but we do, just like in the work from the 70s on sound localization, we'll do generalized cross-correlation to have everybody vote for the right location in a small window. Great. Any other questions? Okay. In that last video, I think what was really interesting was the camera pose indicated the sound direction. And we wanted to see if we could, we were inspired by this idea to see if we could create motion estimation models that jointly learn through localizing sounds. Here's what I mean by this. When you're in a room and you move your head, the images and sounds change in geometrically consistent ways. So I rotate my head to the right, a sound in front of me will become louder in my left ear. And because the images and the audio are changing in this consistent way, we wanted to see if we could simultaneously train a sound localization model and a camera rotation estimation model. In particular, if my change in my visual rotation should be consistent with my predictions of the sound direction in these two different views. The rotation direction between at times S and T should be the difference between the sound direction at positions S and T, at times S and T. And similar to like a structure for motion algorithm, we can come up with a loss that trains this visual rotation and this audio localization to be self-consistent with each other. My predicted sound direction at time S should be consistent with my predicted direction at time T after I apply my visual camera rotation. And there's some ambiguities here I won't go into. For example, it's hard to tell if something's in front of you or behind you, similar to like chirality and structural motion. And so you need to deal with these ambiguities. There also is an ambiguity where you could just assign 0 to everything, which we deal with by adding a cue that says that sounds should be consistent with simple binaural cues. If something is on your left side, it should be louder than your left ear, and vice versa. And we just train the model on simple simulated scenes where there's camera rotation and binaural sound recordings in both time steps. And even though it's trained on simulation, what's exciting is you can apply it to real video. For example, here, my student Xiang rotated his camera and recorded this desk, and you can see the model. Models independently, we can take the visual rotation estimation model, apply it to a data set that is obtained from panorama images with ground truth rotations. And while our model, not as effective as the classic SIFT matching plus ransack pipeline, it's pretty good on this data set of Stanford 2D, 3D. It got about 1 degree of estimate error, even though it was not explicitly given any supervised labels for rotation. It's just implicitly learning them by having them be consistent with the sound direction. Okay, so I'm talking about sound and motion. I want to talk also about tactile sensing as another form of supervision. This is, I think, probably for humans arguably the most important sensory modality. If you lost your sense of hearing or your sense of sight, you would be actually much less impaired than if you lost even part of your sense of touch. People who lose like even their sense of pain, for example, will have really trouble like having basic survival or interacting. Unfortunately, most of the work, or maybe fortunately, depending on audience, mostly deals with robotic tactile sensing. This is the work that Dinesh and I did a few years ago, where we have a robot that's constantly just picking up objects and getting a visual and tactile signal together. And well, it's nice in theory to have the robot collecting data nonstop. Unfortunately, the robot has a very limited view of the world. It really only perceives things that are on a tabletop or a limited environment where it can safely go. And it's also kind of a chicken and egg problem. In order to interact with this, in order to get touch sensing data from this object, you have to like already be able to interact with it, which is unsatisfying. And I think there's a much better way to collect tactile sensing data than robots, and that's with undergrads. So we wanted to see if we could collect a paired vision and touch sensing data at a much larger scale than had been done before. These 3 amazing undergrads in my group just walked around and recorded an egocentric video and simultaneously touched all of the objects they could with this touch sensor called gel sight. You're seeing here a visualization of a deformed gel, which is capturing the shape of the objects they press as they exert force on them. And so you can see they just walked around, collected all the data they could with images and paired touch. This allows us to do multimodal learning with vision and touch at a larger scale. And so you can see they went all around Ann Arbor, they went to parks, they went to playgrounds. At one point, they got politely told to leave a museum. And all in all, they got about 14,000 tactile probes about 4,000 different objects. And once you have this data, you can use exactly the same algorithms that you consider for vision and sound or vision and language. For example, you can train a contrastive learning model to put images and touch and a joint embedding space. Learning, for example, that this touch signal corresponds with this real visual signal. And it doesn't correspond to this other tactile signal that came from the world. And I think, while it's a preliminary finding, I think it's exciting to see that the features that we learned this way through contrastive learning generalize better on a robotic touch sensing task, our previous work on RAS success prediction. In other words, we were able to take the features we learned from touch through this contrastive learning, and we found they outperformed a model that was trained on just pre-trained using ImageNet features, which is the standard feature that people use in touch sensing. And so it's a preliminary result, but it's interesting to see that just having large-scale human collected data seemed to allow us to generalize better, even when the task we're approaching was a robotics task. And you know, this also lets us do a lot of other things that you see in multimodal learning. For example, we can train a diffusion model to take touch, this signal here, and generate an image to go along with it. So this is the prediction of the image that went from this touch. This is the for reference, the true image it came from. Another example, take this tactile signal from wood. We can generate this image. It's a plausible thing that we could have touched to go from this touch. And we have some tricks that make it so the hand is generated these images as well. And a fun application that I like is tactile-driven stylization. You can take an image and make it feel more like a given touch signal. So we can take these coarse bricks and make them feel more like this touch signal that came from these smooth bricks, and obtain a result like this just using standard multimodal image synthesis methods that have been developed for language. Here's another example of this. We could take this smooth table and make it feel more like this soft coat. You can get this result. Okay, so far, I've talked about several lower level modalities. Instead of language, we have motion, sound, and touch. But can we go lower? Are there other, even more low level sensory modalities we could use? Well, what if behind this image, there was actually a sensor that took the photo? What about the sensor itself, the camera that took the photo? Can we learn representations that capture these low level details? Well, this is a task that's very, very important in a lot of applications. For example, in camera calibration, you really need to be able to understand the optics of the camera. Other tasks like image forensics, you need to be able to detect subtle mismatches between the statistics of a generated image and a true image. But by and large, the work on multimodal learning has been about high-level perception. Is there some way we could do multimodal learning to capture these low-level camera properties? Well, interestingly, there's this kind of secret modality within images. In every photo you shoot, there's so-called EXIF metadata that is embedded by the camera inside the photo. And this contains information like the camera manufacturer, Nikon, for example, the focal length, the exposure. And what if we just use this metadata the same way you would with other multimodal learning tasks? And this is work that was led by Chin Hao, who's visiting Penn this semester. So he's an undergrad at Michigan. And our idea was to just train to learn joint embeddings between images and their corresponding camera metadata. So we'll just take the image, we'll take its corresponding EXIF metadata, and because we didn't really want to come up with a new representation for metadata, we'll just convert it to a big string. It's human readable. We'll just convert every EXIF tag into a piece of text and concatenate them together and process them using a transformer architecture that was developed for language. And then we can just learn joint embeddings between image patches and camera metadata. Our model looks almost identical to CLIP, but instead of getting language data as supervision, we're getting this text that's derived from EXIF metadata. And we'll make the image patch very similar to its own metadata and dissimilar from every other. Yeah.
Yeah, like what is the intuition behind like matching the images and metadata together? Because to me, you're kind of like it seems like the metadata is like a very specific modality, and it seems like you're almost like overfitting like the general like image data to like some very specific characteristics. Like that would maybe impact generalization.
Yeah, that's a great question. Thanks, Ed. So I agree that in a lot of cases, this isn't what you want. Like you actually want to have invariance to the camera that shot the photo. If you're trying to recognize dogs, you probably don't want it to be a model that only works on iPhones or kind of knows about the camera. But there are a lot of low-level tasks, like in 3D reconstruction, where you need to know the focal length of the camera. You need to know the optics of the camera. And there are a lot in forensics tasks, for example. There are a lot of tasks where this kind of low-level understanding can be very useful. And for those tasks, I'd imagine that this representation would be perhaps more useful than like ImageNet features, which discard the low-level information. To give some concrete examples of this, we did a really simple radial distortion estimation with synthetically distorted images, and we found that these features seem to outperform ImageNet features on a linear probing experiment, perhaps just because ImageNet like discards the relevant information at this feature scale. And then on an image splice detection task, like is this image real or is it fake? We also get an improvement over ImageNet features. And that makes sense too, because if you spliced an image together, you've taken two different images and combined content from them, you'll have a mismatch in camera information. So for example, if I took this image, which we got from Reddit, and somebody on Reddit, for some reason, spliced in this Elmo character in the background, the splice will have unusual statistics. This part of the image will have the statistics from one style of camera. This one will have the statistics from another style of camera. And we can actually do kind of a zero-shot splice localization. We can compute features for every patch of this image using our learned feature representation. We're not using the EXIF tag, to be clear. We're just taking every single patch, passing it through the visual side of this model, giving us a feature representation out. And you can see this Elmo character, like the statistics of its features seem to be very different according to this PCA visualization. And in fact, you can just cluster these patch features. You can just use normalized cuts to cluster the patches in this image, and it will, in this case, will reveal that this region here is one cluster and the rest of the image is another cluster. And so you can localize the splice using this approach. And it seems to work on par with other state-of-the-art self-supervised splice localization methods, even though it's trained in this very simple way. You're computing these patch features and then using a clustering algorithm. Like here's an example of this from one of the splice detection data sets. You have an input image like this, and Shenhao's model here found that this person was spliced into the image, and this matches the ground truth that someone added this person or vice versa to this. And so one of the things I think is really interesting about these fake images is, I don't know, at first glance they look pretty real. We think that they've kind of fooled us at first glance to think that they're real. And the example of these images that kind of fool the human eye, confusing real and fake. And there are also a lot of other kinds of images that fool humans. So one that we're very interested in are optical illusions. For example, rather than just trying to fool someone into thinking this image is real, we can try to fool them into seeing something different from what's really in the image. For example, this painting from the 1590s. This looks like a basket of fruit, but when you spin it around, you can see simultaneously it's also this kind of creepy head as well. And my students, this was led by Daniel Gang and master student Aaron Park. We wanted to see if it would be possible to create these optical. After all, generative models are really good at making really high quality images that fool people into thinking they're real. Can we repurpose these same models to apply them to creating optical illusions. And of course, the optical illusions have a long history in computer vision. They're often a source of creating tricky examples that will fool a physically based computer vision system, or there'll be a way to kind of model human perception. They're also maybe very close in a very closely related way, a really useful experimental probe for perception systems. Like adversarial examples, for example, can tell us whether the image, whether the perception system that we've trained is a close match. And also another current where it actually affects image that had very similar approaches to generate images, generating optical illusions at the same time. Thus, most similarly, perhaps at Berger and all. And so here's what we're going to do. We're going to consider a generative model as a proxy for human perception, and we're just going to try to subvert it. We're going to try to create an image that has multiple interpretations under a generative model. So here's how this is going to work. We're going to take a diffusion model, and if you remember diffusion models, they'll take a noisy image, and at each step of the reverse diffusion process, they'll remove a little bit of noise from that image. So what if we take our noisy image and we process it in two different ways? We'll have two different views of this image. For example, one that's just the identity, another one that's flipping the image upside down. And we'll prompt the model differently in each of these two different views. And the first one will give it a string that says an oil painting of people at a campfire, another one that says an oil painting of an old man. That'll give us two separate noise estimates. We'll undo our transformation and average those noise estimates back together. And that gives us results like this. We can take this image that's been generated by our model, and we can flip it upside down and get an oil painting of an old man. Here's another one. Looks like a drawing of a penguin. Can anybody guess what the other side would be? The giraffe. And you might ask me why this works. Well, in diffusion model, you're iteratively estimating noise at a sequence of time steps. And at each time step, we require the image to have a certain noise level. Your input is an image that's scaled by a weight factor plus noise that's scaled by another weight factor. And this noise is always just Gaussian IID. And when you flip the image, you can model that as a linear transformation that we're applying to the input, and due to the properties of linearity, you end up with a result like this. And so we're still able. We're feeding the model an input like this rather than a normal input like that. And in our particular case, this flip is a permutation matrix, which is orthogonal. And so the distribution of the noise after this transformation is still in distribution of the model. It still remains Gaussian with identity covariance. And this permutation is a very useful special case. We call it a visual anagram, where you're scrambling the pixels, moving them around. That allows us to do a lot of really interesting illusions. For example, one of these, after we realized that this should work with any with many permutations, we created this idea of a polymorphic jigsaw puzzle. It's a jigsaw puzzle that has two different solutions. For example, here you see an oil painting of flowers. This is actually composed of virtual jigsaw puzzles, and when you rearrange them, you end up with this this picture of this animal. You can see what it was.
And how did you put into the system the boundaries?
Yeah, so the Daniel Gang, the PhD student who led this, by hand just defined those two jigsaw theories. But it's actually a kind of hard like combinatorics problem to do, to create a jigsaw puzzle that works in two ways. So as an aside, that's actually a very good question. Here's another example. It looks at first glance like a painting of houseplants. But then if you rearrange it, you end up with a painting of a deer. And you can see actually this row is unchanged. So when we go back, that actually doesn't change.
So Andrew, in these cases, you're prefixing the transformation between like individual pieces in the original.
Exactly.
Okay.
So we have to define this view function.
Yeah.
That's similar to the matrix A.
Gotcha.
And Daniel just thought about, you know, how can I make a jigsaw puzzle that has two, where I could rearrange the pieces in two ways and they still fit.
Yeah.
But you can also do it with like squares. So example, this looks like an oil painting of a young lady. You rearrange the squares. You get a painting of an old woman. A painting, go back, and then another one, a painting of Thomas Edison, and this one is composed of a whole lot of different squares. You can rearrange them and get a painting of a ball. In the extreme case where you have like a million squares, this would actually be very easy. You also have full palettes to work with. It becomes arguably harder when you have these larger pieces to go around.
So does it always work?
Um,
Feels like such a hard.
yeah, so
You're just like giving random prompts in language and.
that's a great question. Yeah, so I think so we found that like basically the set of illusions it works with really is like the orthogonal matrices. It's like if you deviate from that even a little bit, it just doesn't work.
No, that I
For the
understand.
prompts,
But I'm about the prompts, yeah.
well, it surprised me. I thought like maybe you could, you know,
Yeah.
for example, bilinear sampling doesn't. You have to have a nearest neighbor permutation. But for the prompts, yeah. So there's a lot of trial and error. So I think there are some heuristics. For one thing, you can see there's almost always like an abstract expression like oil painting or pop art. We found it was much easier to create convincing optical illusions if they're the style. We also found faces work relatively well, perhaps because people are it's very easy to perceive a face and something even when there isn't a face. And we also, in our experiments, we just randomly pair different objects together, and some consistently work, some don't. But I think it'd be a really interesting research area to dig into that. There's another one, it's like oil painting of Marilyn Monroe, kind of inspired by Odoliva's hybrid images. You can rotate the center, and you can get an oil painting of Albert Einstein. Painting of a chair becomes a painting of an old man. And then it's also inspired by this work, this famous painting called The Ambassadors. If you look, it looks like an old painting, but if you look very closely, you'll see that there's this kind of creepy skull in the image. This is from the 1530s. And we can do the same thing. You can do skew illusions. You can take this image, looks like a painting of a person, and then when you skew it, you get like a skull. And as Dinesh was pointed out, like there are some failure cases. For example, a common failure case is just have two objects not connected to each other. And we also found that if you deviate from this this theory, you end up with it'll often like fail very quickly. Even if, for example, if you do bilinear sampling, when you do the rotation instead of nearest neighbor, the noise isn't correlated. It doesn't work. But you know, once we had that underlying theory, we realized there are a lot of other maybe non-obvious illusions that would work. So the one that I really like is color inversion. This looks like a lithograph of a teddy bear. And then if I invert black and white, which is just a negation in this color space, then I get something else. I get a lithograph of a rabbit. And maybe these exist, but I haven't seen, not aware of other illusions that work. Here's another one, a lithograph of houseplants. Negate it. It'll lithograph the landscape. And this works perhaps because the white of the peaks distinctively looks like a landscape. And finally, I just want to show our 3-view illusions. This also generalizes the 3 views. For example, this looks like a painting of waterfalls. I think it works, you know, I'd say it's not as strong as a 2-view illusion, but if you get waterfalls, and then if you rotate this, you get painting of a teddy bear. Rotate it one more time. Painting of a rabbit. Ears are here. It's there. One final one. Painting of houseplants. Painting of Elvis. Can people see that? The hair is here. And painting of Albert. All right, so just a few takeaways. I've printed a lot of different ways that you can learn from motion and from multimodal data, and particularly sensory data rather than modality of language. And I've presented some unified methods you can use to find correspondences, either in space or in audio. I think these methods are very general purpose, and I'd love to see different uses for them. I also just want to emphasize a lot of the important sensory modalities out there are kind of neglected. There isn't nearly as much work on tactile sensing or metadata, for example, as there are other modalities. And finally, when all these projects, we're developing these generative models, and it's really interesting to see they can be good enough proxies for human visual perception that you can subvert them to create. I want to thank all of the students and collaborators on these projects, and also thank you.
Open up for some questions.
The cycle consistency is really very beautiful
Okay.
idea. The last one, like a semantic variance there. That
Oh yeah, I guess so. Yeah.
apply a group transformation of
Very
just a
good.
different data. But in the cycle consistency, there are a lot of works right now. Can you put it a little in context to, there are many works like tracking everything everywhere and
Yeah.
and the dense particle video, and all of them really create quite nice tracks.
Yes.
So what is the challenge? I see here that this is the first principle of data association.
Yes.
What first principle do you think it would make the most successful tracklet?
That's a really great question. And actually, our group, we're working on a follow-up now that would be posed to address problems like the tracking any point work or the particle video revisited. And I guess, from my perspective, all these tracking problems are very closely related to one another. For example, if you take an optical flow network and just apply it to the particle video task, it's pretty good if you do it carefully. I mean, it's not as good as their model that's been trained for it, but there's some, they're all kind of quite similar to each other. And in fact, they're often trained on the same sort of synthetic data. So, but the challenges in those problems are slightly different because they're looking at, they actually take more than 2 frames input. So the key difference, I think, in particle video is you take 8 frames of input instead of 2, and you look at them holistically. But we found actually it's not out yet, but I will say that we can get pretty good results on benchmarks like TapVid, which is Carl Dorsch's work on tracking, and they're not as good as the supervised approaches, but we can do pretty well. And I think at the end of the day, the underlying assumption behind the cycle consistency is persistence. Like the same objects are in frame T and T+1 most of the time, and so if you force there to be cycle consistency, then you can exploit persistence as a learning signal. And I think that seems to be true in these tasks as well, though maybe less so when you deal with really crazy occlusions. So that I think that would be kind of the key challenge with really squaring 2 lines of work is how you handle occlusions, which violate the underlying cycle. But I think that our goal is to have these kind of large scale unsupervised models, even you could fine tune using those approaches. And we found that like you can really, like a lot of the architectures are actually quite similar. Like PIP is basically just raft extended to 8 frames. Thanks. Yeah.
So on the touch stuff, right?
Yeah,
You were using gel side sensors,
that's right.
and gel side sensors are, I mean, in our experience together working, but also generally, they are quite fragile.
Yes.
So you would have had to change out many different gel side sensors over time, etc. Each of them will have slightly different characteristics. Potentially, they will have slightly different dot patterns.
Yes.
So to what extent does that affect the approaches that you needed to learn good visual tactile features?
Yeah, so as Dinesh is pointing out, these touches are still kind of fragile. Not quite as extreme as the project we did together, where we would break one of those like every week when the robot would pick up a can of soup or something. But they do degrade over time, and we constantly were swapping out the gel. But we also waited until it was really, really degraded before we did the swap, because in my view, that's just part of the game with touch. Like you need to be able to deal with degraded sensors. If you only work when things are pristine, then that's not great. And then I'm hoping that by having these self-supervised learning models, you can learn features that have seen every variation of the sensors that are out there.
Yeah, like another interesting thing with touch is that there's not really a one-to-one correspondence between the visual input or even the object and the touch sensation that you get from it. It kind of depends on what the forces are that you're applying. Is there a shear, and so on, right?
Mhm.
So did you have to like kind of standardize a procedure for collecting these tactile imprints or?
Yeah. So that's a great point. So I guess there's different ways the vision doesn't correspond. For one thing, so I would say that the motion of the hand might indicate some of these things. So there might be shear force in the video that you see by moving their hand that it's there, and that by correlating touch with sight, you would learn that hand motions correspond with shear force. So I think it is present in the video, albeit very subtle.
Right.
And then I would hope that by training on that data, you would then learn about shear force. But that being said, there is some level where you just can't precisely like figure out exactly where the bump should be based on the image. And there's some fundamental mismatch there, but I don't know if it's that different from like a touch to image mismatch. Like these generative models can handle really, really complicated differences between modalities and at least generate a plausible image. Give me some hope.
All right, I think we're out of time, but thank you. Thank you.